So we're going to talk about interior, closure and boundary of a set inside a topology in this section. Now, these concepts are closely related to open sets and closed sets. So this will be another way to characterize open sets and also to characterize closed sets. So the first definition, we'll talk about the interior first. So we have a topological space, and we'll just take, without writing xt be a topological space, we'll just say let x be a topological space. So I will take, let A be a subset of a topological space X. Now it is understood that there is a topology in X. Now a point X inside A is an interior point of A if there is an open set O containing X and contained in A. So if you want to write this, that means if you take X is called an interior point if you can find an open set such that X belongs to O, where O is a subset of O. We can draw a nice picture. So you have your topological space, you have this set X A. Now X is an interior point if you can find an open set inside A which contains X. Now another way to think about this as, so if X is an interior point, we can think of A as a neighborhood of X. And if I collect all these interior points, we call it the interior of the set. The set of all interior points. All interior points of A is called the interior of A and denoted by, now this is not a standard, so we usually use, in some books we use INTA for the interior. Some books they use A and a small o as an index. Okay, we'll take an example. So if I take a set, say A to B, so the first thing is we need to have a topology. So I'll take R with a standard topology, with the standard topology. Now my set A, we can take, so we'll take the closed interval 1, 2. To have 1 and 2. So I want to find, so if I take a point inside the interval, say I want to take X inside 1, 2, then I can always draw I can always find an open interval that contains x and it's within 1 and 2. So if I take any point other than the endpoints, these are going to be interior points. So I know that, so 1 2 is going to be a subset of interior of A. That's clear. Now we want to check the endpoints. So if I look at 1, now is 1 an interior point? So we put a definition. Can I find an open set, in this case an open interval, that contains 1 and contained inside A? And you can see that this will go outside the set. So I cannot take 1 as an interior point. So that means, and similarly 2 is not going to be an interior point. So this means interior of A is going to be the open interval 1 2. And the next definition, we notice definition, we wrote this down a couple of times. This is the definition of a limit point, but we'll write it again because this is needed for defining the closure. So I will have, let X be a topological space and A a subset of X. Now a point X in capital X is a limit point, is a limit point of A if every open set containing X contains a point of A distinct from X. So if I draw a picture, so we have, so you have this set A and say X is here, and the definition says a point X is a limit point of A if every open set containing X. So this, you need to be a little bit careful because the word every, so if I take any open set containing X, so this is an arbitrary open set, and then there should be an intersection with A other than at X, and this should happen for, so if this is one open set and if you have another open set that contains O, so this is auto, this one also should have a non-empty intersection. And if I collect all the limit points, the set of all limit points of A is called the derived, okay, is called the derived set of A, and we use, since derived, it's like, it's not the derivative, we use the derivative notation A prime to indicate the derived set.